Algebraic properties of logarithms. Hello everyone. To begin, let's look at our first slide. In our previous lessons, we established the fundamental relationship between logarithms and exponents, defining the logarithmic function as the inverse of the exponential function. Now, while the basic definition, which states that log base b of a equals x if and only if b to the power of x equals a is the essential foundation. Simply knowing this definition isn't enough when we move into more advanced mathematics. As we progress toward calculus, we find that we need a specific set of algebraic rules to manipulate these expressions more efficiently. Over the next few slides, we will explore these properties in detail. These rules are incredibly useful because they allow us to simplify complex logarithmic expressions, solve challenging equations, and properly prepare functions for differentiation, which is a key component of the calculus work we will be doing. The product rule. Now that we have established the fundamental definition of logarithms as the inverse of exponential functions, let us move into the practical tools you will need for calculus. We begin with the product rule. Looking at the mathematical statement on the slide, the product rule states that for any positive real numbers b, p, and q, where the base b is greater than 0 and not equal to 1, the log base b of the product of p and q is equal to the log base b of p plus the log base b of q. To understand why this works, we need to remember that logarithms essentially track exponents. If you recall your exponent laws, when we multiply two powers with the same base, for example, b to the power of m times b to the power of n, we add the exponents to get b to the power of m plus n because logarithms are the inverse of this process. It follows logically that the logarithm of a product is the sum of the individual logarithms. Let us apply this concept to a practical example. Suppose we want to simplify the expression log base 10 of 100 times 1000. First, let us identify our components. In this case, our base b is 10, our first value p is 100, and our second value q is 1000. Next, we apply the product rule. Instead of multiplying the numbers first, we can split them apart. The expression becomes log base 10 of 100 plus log base 10 of 1000. Now, we evaluate each term individually. Since 10 squared equals 100, the log base 10 of 100 is 2. Similarly, since 10 cubed equals 1000, the log base 10 of 1000 is 3. Finally, we simply sum these results. 2 plus 3 equals 5. To verify this, we can do the calculation the long way. 100 times 1000 equals 100,000. Since 10 to the power of 5 equals 100,000, the log base 10 of 100,000 is indeed 5. Both methods give us the same result, but the product rule allows us to handle much larger or more complex numbers with ease. As we move forward, keep this relationship in mind. Multiplication within a logarithm transforms into addition. This will be very helpful when we look at the quotient rule in the next slide, which handles division in a similar fashion. The quotient rule. Now that we have covered the product rule, let us move on to the next fundamental property, the quotient rule. Looking at the mathematical statement on the slide, for any positive real numbers b, x, and y, where the base b is greater than 0 and not equal to 1, the logarithm base b of x divided by y is equal to the logarithm base b of x minus the logarithm base b of y. To understand why this works, let us look at the conceptual breakdown. Similar to the product rule we just discussed, this property is derived directly from the laws of exponents. You may recall that when we divide two powers with the same base, we subtract the exponents. For example, b to the power of m divided by b to the power of n equals b to the power of m minus n, since logarithms essentially track these exponents. The division inside a logarithm becomes subtraction outside of it. Let us apply this to a practical example. Suppose we need to simplify the expression logarithm base 2 of 32 divided by 8. We will solve this using a step-by-step approach. First, let us identify the components of our expression. Here, the base b is 2, the numerator x is 32, and the denominator y is 8. Second, we apply the quotient rule. This allows us to split the division into a subtraction problem, rewriting the expression as logarithm base 2 of 32 minus logarithm base 2 of 8. Third, we evaluate each of these terms individually. We know that 2 to the power of 5 equals 32, so the logarithm base 2 of 32 is 5. Similarly, since 2 to the power of 3 equals 8, the logarithm base 2 of 8 is 3. Fourth, we simply subtract the results. 5 minus 3 equals 2. Finally, we can verify our answer. If we perform the division inside the parentheses first, 32 divided by 8 equals 4. The logarithm base 2 of 4 is indeed 2, which confirms our result is correct. Now that we understand how to handle products and quotients, we are ready to move forward to the power rule, where we will learn how to deal with exponents within the logarithmic argument. The power rule. Now that we have discussed how logarithms handle multiplication and division, let us move on to the third fundamental property, the power rule. Looking at the mathematical statement, for any positive real number p, a base b greater than 1, and any real number n, the logarithm base b of p raised to the power of n is equal to n times the logarithm base b of p. To break this down conceptually, this rule essentially allows us to bring down an exponent from the argument of the logarithm and treat it as a coefficient multiplying the front of the expression. This is an extremely useful technique in calculus, particularly when we need to differentiate functions where the variable is located in the exponent. Let us apply this to a practical example. We want to simplify the expression, the logarithm base 10 of 10 to the power of 5. To solve this, we will follow a step-by-step process. First, let us identify the components of our expression. The base is 10, the argument is 10 to the power of 5, and the exponent n is 5. Second, we apply the power rule. By moving the exponent to the front, the expression becomes 5 times the logarithm base 10 of 10. Third, we evaluate the basic logarithm. We know from our previous studies that any logarithm where the base and the argument are identical equals 1. Therefore, the logarithm base 10 of 10 is equal to 1. Finally, we perform the multiplication. 5 times 1 equals 5. With the product, quotient, and power rules now established, we have the tools to manipulate most logarithmic expressions. In the next slide, we will discuss how to handle situations where the base is not convenient, using the change of base rule. The change of base rule. Now that we have mastered the product, quotient, and power rules, let us move on to the final essential property, the change of base rule. Looking at the mathematical statement on the slide, the rule states that to change log base a of p to a new base b, the formula is log base a of p equals log base b of p divided by log base b of a. To break this down conceptually, this rule tells us that the ratio of the logarithms of a number p and a base a remains constant, regardless of which new base b we choose to perform the calculation. You might wonder when you would actually use this. Let us consider a real-world application. Imagine you need to find the numerical value of log base 2 of 7, but you are using a standard scientific calculator that only has a button for the natural log, which is written as ln. To solve this, we can follow these steps. First, identify the original components. The original base a is 2, and the value p is 7. Second, we choose a new base that our calculator can actually process. In this case, we will choose base e, which allows us to use the natural logarithm. Third, we apply the change of base formula. This transforms log base 2 of 7 into the natural log of 7 divided by the natural log of 2. Fourth, we use the calculator to find the decimal values. The natural log of 7 is approximately 1.9459, and the natural log of 2 is approximately 0.6931. Finally, we divide these two values, which gives us a final result of approximately 2.807. This rule is incredibly useful for computation, but as we move to the next slide, it is important that we discuss some common mistakes to avoid, as it is easy to confuse these logarithmic properties with standard algebraic distribution. Common mistakes to avoid. Now that we have explored the fundamental rules of logarithms, it is crucial to discuss some common pitfalls. Even though the rules seem straightforward, it is very easy to misapply them. Let's look at the most frequent mistakes students make. First, let's address the mistake of distributing logarithms over addition. A very common error is assuming that the log base b of the quantity x plus y is equal to the log base b of x plus the log base b of y. Please be careful here. This is incorrect. As we discussed in our section on the product rule, logarithms turn multiplication into addition, not addition into addition. There is no simplified identity or rule for the log base b of x plus y. Next, let's look at the power rule we covered previously. Students often confuse the log base b of p raised to the power of n with the entire expression log base b of p raised to the power of n. It is important to remember that the power rule, which allows us to bring the exponent down as a coefficient, only applies when the exponent is specifically on the argument, p. If the entire logarithmic result is being raised to a power, the rule does not apply, and you cannot simply move that exponent to the front. Finally, there is often confusion regarding the quotient rule. You might be tempted to assume that the log base b of x divided by the log base b of y is equal to the log base b of the quantity x minus y. This is a significant error. Dividing one logarithm by another is actually a change of base scenario, which we just covered in the previous slide. The quotient rule only applies when the division is happening inside the argument. To be clear, the log base b of the fraction x over y is what equals the log base b of x minus the log base b of y. By keeping these distinctions in mind, you will avoid the most common errors in logarithmic manipulation. Now, let's move to our final slide to summarize all the key takeaways from this lesson. Key takeaways. To wrap up our session on the algebraic properties of logarithms, let's review the key takeaways from the slides we have just covered. First, we have the product rule. As we discussed, the formula is log base b of the product p times q equals log base b of p plus log base b of q. The key idea to remember here is that multiplication within the argument transforms into addition. Next is the quotient rule. The formula states that log base b of x divided by y equals log base b of x minus log base b of y. Similar to the product rule, the core concept is that division within the logarithm corresponds to subtraction. Then we have the power rule. The formula is log base b of p raised to the power of n equals n times log base b of p, as we saw in our examples. This allows us to move the exponent down to become a coefficient, which is incredibly useful for simplifying complex functions. Finally, we have the change of base rule. This is expressed as log base of p equals log base b of p divided by log base b of a. The key idea here is the ability to switch to a more convenient base, such as the natural log, which is essential when using a standard scientific calculator. I strongly encourage you to keep these 4 rules in mind and refer back to the slide on common mistakes to ensure you are applying these properties accurately in your practice problems.